Now we are going to discuss the fifth unit, which is mainly about power converters or power electronic circuits. In this chapter, we are going to study electric circuits, various electric circuits used in electric vehicles. As we know that all the energy flow within an electric vehicle is in the form of electric current. Hence, a large number of electric circuits will be required in order to control the operation of electric vehicles. These circuits they are commonly known as power electronic circuits or power converter circuits, as they handle large amount of power as required for the operation of electric vehicle. There are several power converters used in each of the electric vehicles, and each power converter has a certain role assigned to it, certain function to be performed in the process of supplying power to the electric vehicle wheels so that it can drive the load. Let us check this particular diagram here visible. This is a schematic diagram of an electric vehicle, and it shows several blocks, the block diagram as well as the schematic diagram, and most of these blocks, they are about the power electronic converters or power converter circuits along with the battery and motor. So this is a motor, this is a battery, okay, and all other circuits, they are basically the blocks are the power converter circuits. So there are several number of power converters used, as we can see from the diagram, for each of the electric vehicle. What roles they are assigned? So let us observe. For example, we have here a traction battery, and naturally as the electric vehicle is in operation, we need to charge the battery. So for charging the battery, there is a pair of converters, power converter circuits. First one is AC to DC converter. So it's a sort of a rectifier, and then it is coupled with an isolated DC to DC, which is a kind of a isolation between the AC powered rectifier and a traction battery to prevent any damage. So isolated DC to DC converter is required. So these two converters, that is AC to DC converter and then DC to DC converter, they form the charging system. We need to charge the battery as the vehicle is used. This is one of the roles for the electric circuit. Then second, we need to supply this electric motor with the power. So as we have seen that there are various types of motor, especially brushless DC motor and switch reluctance motor or permanent magnet synchronous motors. All these motors, they require a multi-phase supply. So for generating that, three-phase converter is used. Three-phase, or we can also have a multi-phase converter. And the purpose of this converter is basically DC to AC. The battery power coming from the traction battery is the DC power, and it will be converted into a pulsating three-phase voltages for the operation of motor. So we require DC to AC converter, right? So three types of converter already we are seeing: AC to DC and DC to DC, and then again DC to AC, which is also known as an inverter. Apart from this, the electric vehicle also have auxiliary battery. The function of auxiliary battery is to provide the supply for the operation of some essential elements of the electric vehicle, like the lights or indicators, or sort of a auxiliary power supply required for controlling the for the controllers, okay. And apart from that, for supplying the power to the auxiliary battery, we need to charge it, and hence there is a auxiliary DC to DC converter. So there are several auxiliaries like air conditioning unit and power steering, and then thermal management systems. All those also require low voltage DC supply, that is again derived from the battery using DC to DC converter. So here itself we can observe that there are several circuits, AC to DC or rectifier, DC to DC, or they are also called as a chopper circuits, and then DC to AC for supplying power to the motor. So these are inverters, and then low voltage DC to DC. So many a times this can be the battery pack is generally a high voltage battery pack. So we need to step down the voltage. So this is a kind of a step down DC to DC converter, and the supply charging point we have AC to DC rectifier is a low voltage circuit again. So this here isolated DC to DC converter, there is a step up of voltage. So this is a kind of a step up DC to DC converter, and this auxiliary DC to DC is a step down type of DC to DC converter. So various combination of converter circuits are required for stable operation of electric vehicle, and this particular diagram, it indicates mainly the power converters which are used in the battery electric vehicle. You can see only source, energy source or storage is a traction battery. Now let us move to the next slide and kindly observe yet another schematic diagram. We can see that of an electric vehicle. So in the middle we have got a battery, and a battery storage is there. So for this battery storage is connected to here AC to DC rectifier or a converter along with the DC to DC converter. Okay, so very similar the charging, but this is a power converter circuit for a hybrid electric vehicle. Okay, this is for hybrid electric vehicle means that it has got an engine coupled with one axle, and it has got a motor coupled with another axle. So hybrid, it works on both the fossil fuel to some extent, and then also the electric motor. Both the options are available, and these are like optimized. So if engine is used, it can be coupled to a generator, and then engine along with generator, when the car drives on fuel, it will be able to charge the battery while the car is moving. So when a fuel is supplying power to the engine, this fossil fuel, when engine is working, IC engine, it will be able to charge the battery while the car is moving. At the same time, it will be driving the car. And let us say we want to drive the car only with respect to electric mode. So we have seen earlier different types of hybrid electric vehicles are there. So they can be a small hybrid, medium hybrid, or full hybrid type of vehicles. So it will be possible to optimize the operation for this. And battery operated electric vehicle, if we operate only battery, so battery will be supplying power from DC to DC converter, then to the inverter and the motor. Okay, in the absence of IC engine driving the electric vehicle. Just now we have checked with the different types of power converter circuits or electric circuits that will be required in electric vehicle for the overall control and operation. So just to revise, those were of categories AC to DC converters, then DC to AC converter, then DC to DC. These are the three major categories of converters. Now, what are these converter circuits? Let us go into further details, and before we start discussing about the circuits straight away, we would like to understand what are the main components of this circuit. So these circuits are generally power converter circuits. These are designed using high power semiconductor devices. So power converter circuits, they are all designed using high power semiconductor devices such as transistors, bipolar junction transistor BJT, then MOSFET, IGBT. This is insulated gate bipolar junction transistor. And generally all these devices which are called as a power semiconductor devices, these are made using the silicon and germanium, conventional semiconductors. But with the evolution of electric vehicles and the faster control requirement and high power densities, the next generation power electronic devices have evolved. So these are made from mainly two types are now getting a lot of research interest and are being developed for electric vehicles. They are silicon carbide, that is SiC, and then gallium nitride or GaN devices. So these devices are being used for electric vehicle and hybrid electric vehicles, and these are called as wide band gap semiconductors. So these devices, they are called as wide band gap semiconductors. Now what is the band gap? So band gap is basically the energy required by the electrons within a semiconductor to move up the band. So that is what is called as a wide band gap. If that energy required is more, it has to overcome a wider band gap from the unexcited state to the excited state in order to provide the necessary conduction of transistor switches. So let us say here there is a slight comparison shown with respect to the conventional silicon semiconductor. It requires band gap inside a silicon semiconductor is 1.1 electron volt, and as compared to that the SiC requires nearly 3.2 electron volts, and gallium nitride, it requires 3.4 electrons. So nearly this is 3 times the requirement for the silicon. So that is why it is called, it requires larger energy to change its state from off state to on state. So why this kind of setup is used? Because it provides so many different advantages that we are going to see in the next slide. So the various advantages of silicon carbide and gallium nitride devices because of the wide band gap, they are listed here. The very first one is a high electric field breakdown. Okay, first one. So it provides a higher electric field breakdown. Naturally, it has the advantage of withstanding higher temperature. It provides higher thermal conductivity, nearly 3.5 times of conventional silicon semiconductor. It is capable of operating at high frequency, high temperature, and similarly high power levels. It has a faster switching time, and hence it can take decisions very quickly. Switching operation can be very faster, so provides smooth control for the converters and hence the electric vehicle. There is a lesser power loss because of better thermal conductivity. The power losses in the silicon carbide and gallium nitride semiconductors is less. So naturally the design will be very compact design, and it can be used for better efficiency, low power loss, and this is very much indicated here, smaller size, compact. And lastly, it delivers superior performance compared to the conventional semiconductor devices. Now that we have realized that the latest or recent types of semiconductor devices are silicon carbide and gallium nitride, let us see some interesting graphical representation of power electronic devices, power ratings and operating frequency range. So kindly pay your attention to the diagram. The diagram shows on the y-axis the output power. Output power, it's an electrical unit, volt ampere. So we can see that output power is varying from some 10 volt ampere, very low rating, up to, all the way up to 10 megavolt ampere, means it's in megawatts, right? And on the x-axis, if you observe, it is the frequency range. So operating frequency in hertz. So this operating frequency is not the power supply operating frequency, rather it is the switching frequency, how faster the power electronic transistors from silicon carbide or gallium nitride, they turn on and turn off as per the requirement of the application. So this is a complete range. Please observe here, that this complete range of power and frequency is divided into three areas. One here on top left. So top left here, it means that it is a low frequency and high power application, right? These are applications which are managed using silicon carbide. This is most suited for high power but low or medium frequency. It is silicon carbide. Then the second region here belongs to the gallium nitride. This is mainly characterized by high speed or high operating frequency, high switching frequency, but medium and low power levels. And the third one, which slightly we can see all the three semiconductor regions are slightly having some overlap because basically they are all semiconductor devices. So the low frequency, medium to low frequency, and similarly medium to low power range, it is mainly for the simple silicon semiconductors. The diagram shows various types of applications where power electronic devices are used. The low frequency applications, observe low frequency applications where silicon carbide conductor can be used. They are listed here, mainly wind turbine or railway traction supplied to the electric locomotives, right? And similarly the PV inverter used for the power conditioning units, and similarly the inverters which are used in the industry for carrying out the heavy loads, cranes, then heavy lifting. Okay, so these are all basically the power rating for this kind of applications, wind turbine and then electric locomotive, lies in the range of several megawatt. So very high power, and these applications are more suited to the silicon carbide semiconductor. Then we observe somewhere in between these two ranges, we are shown here a symbol of vehicle. So electric vehicle, it requires, the power requirement for this is a medium power. So what does it mean? Medium power means maybe few 100 kilowatt or maybe 10 kilowatt to 100 kilowatt range as per the size of the vehicle. And for this range, the operating frequency also having very similar range as 10 kilohertz to 100 kilohertz worth of operation. So electric vehicle can be designed either using silicon carbide or gallium nitride as per the availability, costing and the requirement. And lastly, we observe on the bottom right side, gallium nitride, mainly known for the lower power, medium and lower power rating, and these kind of ratings we observe in the power supplies for the PCs or laptops. Okay, similarly power factor correction methods or solar panel power micro inverters which are used in the solar panel based power supply, okay, power backup, and data centers, the servers which are used across, they also have some kind of a power supply. So these are all based on high switching frequency and medium and low power rating. So these applications are mainly suited well for the gallium nitride. So this is a very interesting graphical representation of various applications, high power as well as high switching frequency, and both these are more preferred as a new type of devices, silicon carbide and gallium nitride.